All right, maybe we should get started. It looks like we have a pretty good crowd here. So thanks again, Ram, for being flexible and agreeing to do this remotely. So Ram Vasudevan is a assistant professor at University of Michigan, where he has done some really fantastic stuff on the intersection between control and optimization. Research on all sorts of various topics. I had the great pleasure when I was a PhD student for Ram to be a postdoc for a couple of years in our lab, and just having the opportunity to be 10 feet away from him and chatting about all sorts of different topics, bouncing ideas back and forth. I felt like I learned a ton, and so I'm super excited to have Ram here, giving us a virtual grass seminar. So welcome and take it away, Ram.
Yeah, thank you so much. Just as I mentioned earlier, I've made the link to the PDF and the PowerPoint version of this talk available. So if you want to click on that Google link, I posted it on the chat, so feel free to go there. And thank you all for joining. This is a new experience for me doing this virtually. So if you have any questions or something, I'll try to check in sporadically on the chat, but feel free if I'm running over things to sort of step up and ask away at questions. So this talk is really about, sort of this idea of doing sort of infinite dimensional optimization with, sort of a focus on robotic systems. And so, I should start off by mentioning, that the folks who are really doing the heavy lifting are my students, and really our group is particularly interested in developing and applying optimization tools for modeling, estimation, and control of robotic systems with a focus on practical solutions while providing useful mathematical guarantees about the properties of these algorithms that we develop. And so it's pretty broad. And so before I start, really diving into the technical details of a particular portion of our research, thought I would spend a few minutes just talking at a high level about the type of research that we do in my group. And in particular, we're really interested in two different application areas. The first is what I call prehabilitation, rehabilitation, and assistance. And the idea here is that we really want to be able to develop tools that are able to sort of remotely diagnose or improve the musculoskeletal ability of different people as they're moving around in the world. And so actually the last time I was at Grass Lab, which I think was maybe 10 years ago at this point, I actually got to speak a little bit about my PhD work, or what became my PhD work. And it was really focused around this idea of trying to build models of humans as they were moving around and doing it from cameras. And in fact, that work has continued on here at the University of Michigan. And in fact, now what we do is we've actually had the opportunity to work with a sports science clinic. And actually what we've done is sort of completely equipped the setup with a bunch of different cameras. And we've shown that some of the modeling tools that I presented 10 years ago can actually be applied in concert with things like OpenPose to be able to estimate not only sort of the kinematic properties of a person, but the dynamic properties of their behavior as well. And one of the things we've been really excited about is trying to develop diagnostic tools or quality metrics around sort of rehabilitation as it progresses. And so one of the things the sports science clinic is particularly excited about is trying to develop new tools to track the rehabilitation of ACL injuries. And the idea here is that typically people have been focused around the idea of just looking at the energetic efficiency of an individual, and that is seeing if they're able to recover the same sort of energetics that they had, before their injury, as the rehab progresses. And what they found through years of experience is that that is not a very good metric for seeing if the person has actually recovered their mobility and is, far away from re-injuring themselves after a rehab procedure. So one of the tools we've been thinking about is, can we develop metrics that instead of looking at just energetic efficiency, track the robustness of the individual during different types of motion. So the idea here is, if you look at this video down here, you're seeing an individual actually on a treadmill. This is an animation of that individual, but what you're seeing is that we're actually perturbing them. And what we wanted to try to understand is, are there ways for us to assess the robustness of their motion and use that in a clinical setting rather than just energetic efficiency? And in fact, one of the tools that we've developed are these nice sort of region of attraction objects for different types of steady state locomotion. And they look like these sets in state space. And one of the things we've spent a lot of time doing in my group is actually building these really sort of exacting experiments to show that this estimation of the region of attraction of an individual is actually accurate enough to tell us if the types of disturbances that occur in the real world actually correspond to them having to switch control strategies, and as a result, perform sort of less robust types of motion. And in fact, this paper that was just accepted at the Royal Society illustrates sort of that we can actually carefully predict the types of disturbances that a person is able to tolerate and those that they're not able to tolerate. And we've actually started using this metric to track rehabilitation progress over time. And so one of the ideas here, and I'll talk about some of those tools inside of this talk, but one of the ideas here is that we can then translate these types of rehabilitation metrics into different ways that we can assist a person. One of the things we've been really excited about are these sort of soft robotic tools, and they're really, really, nice objects. That is, soft robots, can deform nicely. They can operate in and around people. They don't necessarily cause injury. The challenge is because of their nonlinear properties and sort of their continuum of actuation, they actually are pretty darn difficult to control. And in fact, what I'm going to talk about today is some techniques that look at data-driven sort of methods that are amenable to subsequently forming, or doing control in real time. And so that's sort of one area of research that my group does. The other is really in autonomous and connected vehicles. And in this context, it sort of makes a lot more sort of maybe obvious sense how robotics has a big role here. There's sort of the same challenges, modeling. In this instance, it's like, you modeling a person at great distances. And one of the things we've done is develop these really cool data sets along with Ford of LiDAR information, camera information, all of this stuff calibrated, but now collected at, all sorts of weather environments, and using that sort of information to then predict what individuals will do at different intersections and whatnot. One of the other tools we've developed is sort of improving the quality of SLAM, or our estimation tools that we use to figure out where an autonomous vehicle is in the world. So in fact, in many of these instances, we have several different maps. So for example, that's illustrated here in green and blue that are collected by different systems. And what we want to be able to do is overlay those maps on top of one another. And in fact, there have been a lot of algorithms that try to do this, for instance, things like Ransack. And the challenge has always been that if there are any outliers while trying to do this type of map alignment, it tends to have really, really sort of detrimental effects on the behavior of these algorithms. So what my group has spent a lot of time doing is developing these algorithms that we call pairwise consistent matching. And actually, this paper was presented at ACRA. The code is down here on the right. And what it allows us to do is basically do really robust map alignment, even in the presence of outliers. And in fact, lots of folks have now taken this work and extended it. It's been really exciting. It's had a really nice impact on this community. The last problem, of course, in this sort of space is really trying to do control. And actually illustrated here on the bottom right is a video that I worked with Francesco Borelli at Berkeley when I was a graduate student. This is the first time I went to Michigan. They flew me out to Sault Ste. Marie, which if you're not from Michigan is the topmost part of Michigan. In February, I grew up in Southern California. It was tremendously cold. That was me actually outside recording that video. And we were trying to develop MPC controllers to try to actually get this car to do reasonable things. And I'll talk a little bit about that work as I go along today in my talk. So all of that stuff, seems sort of disconnected and in various different application areas. But really the way that we think about it in our group is that a lot of these problems are united by a perspective. And that perspective is what I'd argue is infinite dimensional optimization. And the idea here is that we can translate nonlinear models or nonlinear dynamics into linear models, but now described in infinite dimensional space. And in fact, what that means is we can translate problems like optimal control or region of attraction computation into convex programs, but now formulated in the space of functions or in the space of measures. And I'm going to talk a lot about that today. And in fact, I'm going to focus really in on this control task. And the idea here is that I'm going to show you a set of algorithms that will allow us to do first, provably safe control of autonomous vehicles, and then subsequently talk about doing, data-driven model identification and control of soft robotic systems. And so what that's going to look like in the case of an autonomous vehicle is something that looks like this. And so this was presented at RSS. And what we're doing here is actually controlling a golf cart system. This is at the University of Sydney. And on the left-hand side, you're seeing a reachable set that is control parameterized and is actually being used online and in order to actually be able to do provably safe control of an autonomous system. And in fact, we've extended this work to a variety of different platforms. For instance, quadrotors. So this is going to be an illustration of this quadrotor here on the left. And there's a really small lab, but we're actually able to do full real-time control of this quadrotor with guarantees about safety, et cetera. And I'll talk a little bit about how that works. But in fact, this is still using that same reachable set type of computation that I described on the previous slide. And in fact, we've actually even been able to extend this work to really high degree of freedom systems like manipulators. So in this example, we have a 7DOF manipulator, which is the fetch robot. We're actually doing real-time control using a reachable set, which is shown on the left over there in light gray. And what we're actually able to do is perform control online with that reachable set representation for this 14-dimensional system in real time. And in fact, that allows us to do things like receding horizon control. So for example, if I have something like an obstacle appearing here, we can actually figure out how to do safe control around that by using these reachable sets online. And in fact, that's what's illustrated on the right again. I'm going to talk about that today. That'll be the first portion of my talk. The second portion of my talk is going to be talking about how we can do data-driven model identification and subsequent control for soft robotic systems. And what's illustrated here is the first example of doing pick and place for a soft robotic system. And in fact, what this system is doing is actually figuring out the mass of these objects down on the bottom right. It has never seen these objects before, but it's going to figure out the mass of that by building an online observer or using an online observer, and then being able to pick and place these objects autonomously. And in fact, I'll talk about how that works. And that'll be sort of the two portions of my talk. So the first part will be this reachability-based trajectory design for provably safe real-time planning for autonomous systems. Then I'll talk about Koopman-based modeling and real-time control of a soft robot manipulator, and then I'll conclude my talk. So that'll be sort of the breakdown. Hopefully I'll be able to get to both parts. If I'm not able to, we can obviously talk about it offline. Okay, so it's been a lot of work on thinking about how to control autonomous systems. Typically the way that people have thought about this in the autonomous vehicles community is by looking at a tri-level hierarchy. The idea here is that you have something like a high-level planner, and if you want to think about this sort of anecdotally, this is like a Google Maps type of planner. So if I want to get from here to Philadelphia, what I would get is sort of turn-by-turn instructions from Google Maps that would tell me, get on I-94 and then keep driving, make a left here, make a right here, etc. Well, in the autonomous vehicles community, they still use the same type of high-level planner, but that is subsequently passed that information to a trajectory planner. And what that trajectory planner tries to do is basically execute or generate trajectories that are able to satisfy those turn-by-turn instructions that are provided to them. That information is then passed into a tracking controller, which is, sometimes an MPC loop, but can be other types of things like a simple PID loop if it needs to be. And in fact, thinking about these systems, back in 2010 when I was a graduate student, we actually used the same sort of hierarchy where we had a path generation algorithm, which was doing trajectory planning, and then we had an MPC loop that was doing tracking control around this path that had been generated autonomously. This was a simple example. It was several years ago. It was us doing a lane change, but that path was generated autonomously, and then we were following that path by using MPC. Now, that's really great. The challenge is that in some instances, you are generating a path that the MPC loop is simply not able to follow because you're outside of the region of attraction of that trajectory that you've designed. And you'll hear me curse here. I'm actually in the back of the car recording this video again. And in fact, in this instance, we actually crashed the car. You'll hear the test driver scream in a second. And in fact, that's kind of the problem here. These types of tracking controller trajectory planner loops can work together with one another, but sometimes they can create problems that are unforeseen because you're not necessarily making any strong guarantees about the ability of the tracking controller to track the plan generated by the trajectory planner. So a lot of folks have thought about how do you bring safety into the picture here? And typically the way that they've done that is by focusing in, for instance, on the tracking controller part of this problem. And really, there have been a variety of different methods proposed to try to validate both the plan or the ability of the tracking controller to track a plan. And in fact, sort of the way that we think about it in my group is that you can sort of break them into three different bins. So the first bin is sort of these algorithms that perform check-in. And what they simply do is to check if a trajectory that has been pre-computed can actually be tracked satisfactorily by a tracking controller. One of the popular methods in this area is using zonotopes to try to do this. And I'll show you what that looks like in this picture here. Suppose this is the state space of the vehicle. I'm showing it sort of in 2D. In this instance, suppose we have some sort of pre-computed trajectory that is, sort of projected into 2D. And, now our tracking controller tries to follow that path. And in fact, there's some tracking error associated with tracking that trajectory. And in fact, what these zonotope methods try to do is to describe the error between that pre-computed trajectory and your ability to track it by using these objects called zonotopes. Then they use those zonotopes online in order to determine if a particular pre-computed trajectory can actually be executed in a way that does not actually intersect with these zonotopes. Now, these methods work really well. The challenge is that they're not actually doing any planning. They're simply verifying that a pre-computed trajectory can actually be executed satisfactorily. So on the other hand, there have been a bunch of different methods that have tried to actually figure out how to use plans online in a way and actually modify those plans if possible. We call these methods sort of correct methods. There have been a family of them proposed in the literature. So one, sort of the popular perspective has been reference governors. This paper by Ilya Kolmanovsky is a really nice tutorial on this idea. Sort of more modern sort of approaches are these control barrier functions approach and the fast track approach. Let me talk a little bit about those approaches since they've been particularly utilized in the robotics community recently. So the control barrier function idea is as follows. So suppose I'm trying to do something like adaptive cruise control in this instance, and I'm inside of a lane, and I'm trying to go forward. And in this instance, suppose some sort of red car appears. So I have a particular trajectory or a control input that I would like to apply into the system. I have a barrier function that is described in the state space of the system, and in fact has a nice characterization in the control input space as well. And in fact, what I can do is solve a quadratic program online to modify my current control input at this instance in time in a way that ensures safety of the system. And in fact, these methods have been really attractive in situations like adaptive cruise control and lane keeping. The one problem with them is that they're myopic in the sense that they're only really modifying the control input at this current instance in time. And they're not really generating a trajectory that, for instance, would go around the red car, okay, like in this example. So to try to address that problem, recently there's been a nice idea called fast track that has been proposed by Claire Tomlin and her students from UC Berkeley. And the idea here is, I treat a planning model or the trajectory planning model as if it is a disturbance into the system. And so the trajectory planner simply generates a plan, and maybe, there's a set of plans that it's capable of generating, and maybe I describe that by using some sort of cone. Now again, what's going to end up happening is that I have a tracking controller, and in this instance, I'm going to treat that as if it is some sort of system that's trying to catch up with this trajectory planner that is some sort of disturbance or some sort of malevolent actor in this instance. And so what I can do then is to solve a type of Hamilton-Jacobi-Bellman style formulation of this problem where I try to find the best possible behavior of that tracking controller while it tries to track any possible behavior of that trajectory planner. And what ends up happening is I generate this tracking error by solving this Hamilton-Jacobi-Bellman equation as a function of the value function that is generated during the solution approach. And then at runtime, what I do is I take the largest possible tracking error, and I basically buffer all obstacles by that tracking error. And then what I can do while generating trajectories at runtime is actually make sure that they stay outside of that buffered zone. And as a result, I can make guarantees about the safety of the system. So these methods are also really interesting. The problem is that by treating their trajectory planner as a disturbance, they typically tend to behave very conservatively. And I'll actually show you what that looks like in a comparison as I go further in my talk. So the last sort of set of approaches, think about bringing safety in at a higher level, which is at the trajectory planner. And in fact, the method that I'm going to speak about today is also going to be focused on bringing in safety at the trajectory planner level. And the way that this is going to work can be best understood by first thinking about how many autonomous vehicle companies actually think about doing trajectory design currently. And the way that they do that is by, instead of thinking about the control input space, focusing on a space of trajectory parameters, okay? And what they do is simply sample from that trajectory parameter space to generate a family of reference trajectories. And then they use this family of reference trajectories at runtime to ensure if they're able to find a trajectory that can satisfy their high-level plan while somehow avoiding obstacles. Now again, as I mentioned, the problem that can occur is that you have some sort of tracking error that can appear while you're actually applying your tracking controller. And so what folks typically try to do in this instance is to compute a reachable set around the control or the tracking controller trying to track that particular trajectory parameter. And this idea, which has been called funnel libraries and has been developed by Ani Majumdar and Ross Tedrake. In fact, when Michael and I were both at the Locomotion Lab. And what they typically do is generate a variety of different funnels. This is usually done by discretizing time and generating a reachable set at each of these discrete time instances. And then at runtime, if you have a particular obstacle that appears in the world, you then eliminate potential trajectory parameters. And this is usually done by applying some sort of graphics processing algorithm, so something like Bullet. Now, the challenge here is that the collision checking is not verified to operate safely, and you've actually picked a finite library a priori. And so what we're going to try to do is to address both of these concerns by essentially building an algorithm that can handle a continuum of trajectories plus error. And we're going to use reachability analysis to do that. And we're going to do that offline. And then what I'm going to show you is a way to actually discretize obstacles in a way that is validated to be correct, and can allow for real-time operation. And that's going to happen online. So I'm going to show you what this algorithm looks like sort of on an arm, just at a high level, and then I'll walk through the specific details as we go along. So the idea here is, suppose I have an arm. What I'm going to do is generate a family of trajectory parameters that are going to, each parameter is going to describe a particular trajectory for that arm. And in fact, what I'm going to have is a family of trajectory parameters, and that's going to describe a volume in the state space or the workspace of this robot. And in fact, what I'm going to do then is identify constraints online and actually map those into what I'll call trajectory space obstacles. And in fact, what I'm going to show you is a conservative way to represent that trajectory space obstacle, so that online what I can do is identify a particular trajectory parameter that satisfies some desired configuration that I want to reach by solving this optimization problem down here. And I'll show you how I can write that optimization problem in a nice way that allows me to do real-time control in a way that actually can guarantee safety. Okay, so that's going to be sort of a high-level description of this algorithm. And in fact, I'll call that algorithm that we've developed Reachability-based Trajectory Design, and I'm going to walk through the details now. But before I do that, maybe I'll pause and just check in if anyone has any questions. Okay, I'm going to assume
it's going great.
Oh, okay. Everyone's good? Okay. All right, so let's talk about sort of the pieces of this algorithm. And so the first piece was thinking about how to parameterize trajectories. And so I'll flip back to the car example, and I'll talk you through how do we actually parameterize these trajectories. In fact, you can choose a variety of different trajectory parameterizations. This isn't really too important. We just require one specific property in the trajectory parameterization. I'm going to talk about what that looks like. So in fact, I could parameterize my trajectories like this, where I could have a particular speed profile that I tracked, and then I brought it down to 0. And I have a yaw rate profile that I try to track, and then I eventually bring that down to some non-zero value. So that could be the way that I parameterize trajectories. And in fact, the really important part is that I need to make sure that at the end of my trajectory parameterization, I actually bring my system to a full and complete stop. In fact, that's going to make sure that I can satisfy some sort of persistent feasibility style result while I do online control of this system. So that'll be the first assumption I make. And in order to describe all of this, I'll focus on dynamics that look like this. So now I have a dynamical system in some state space and described by some control parameter k star in this instance. And again, each trajectory is going to be defined over a finite time interval. I'm going to describe how to select that time interval in a few minutes, but that time interval is going to always ensure that I end with a fail-safe maneuver that is going to be something like bringing my system to a full stop. If it is, a car, and if it's an arm, a similar thing. If it's a quadrotor, it's not going to bring it down to the ground, but instead is just going to bring it to a stop and hover in midair. Okay, and so at the University of Berkeley, UC Berkeley, have shown how to do this by using sums of squares programming. My students have actually developed a nice way to be able to build this bound by sampling the system correctly. And in fact, we've written a paper about that was presented at DSCC in 2019. There are a variety of different ways to build this bound. You could also build a conservative representation of it, for example, by bounding the accelerations that you apply into the system. But we'll make this assumption here. And if you have more questions about this, I'm happy to talk about it maybe after my talk is over. But we're going to run with this assumption. And in fact, what we're going to do is append our original dynamics with this G times D. And this D is going to describe a disturbance that is going to live between -1 to 1. And in fact, the effect of this is that basically we can bound all of the possible behavior of the original system plus tracking error by using this new dynamical system. And in fact, what we're going to do is basically construct this green set here, which is describing this reachable set of the system. But now, instead of just doing it for a single trajectory parameter, we're actually going to do it for a family of trajectory parameters. And that's going to be depicted as the following set. Okay. And so this forward reachable set is what we're going to try to compute next in a nice way. And in particular, what we're going to be concerned about is generating this forward reachable set as a function of the trajectory parameters that we choose. Okay. And so in order to do that, we're actually now going to solve an optimization problem. And this optimization problem is going to be described by optimizing over the space of functions. So in this instance, v, w, and q are going to be functions. This integral here, w, is going to be describing the integral of w with respect to the Lebesgue measure. And in fact, what we're going to show is that w actually converges to the indicator function on the forward reachable set of the system. And in order for that to happen, we're actually going to write down several constraints here. And these constraints are sort of daunting at first, but in fact, what you can show is that v is actually acting like a Lyapunov function for the system, in that this first constraint here is basically describing that the function decreases along trajectories of the system. And in fact, what this Q function is doing is bounding the possible error that can appear according to that disturbance term in the system. And in fact, what we can show is that if any feasible solution to this linear program, and I should have mentioned, this is a linear program because V, W, and Q are functions, but these constraints here are basically pointwise constraints. And in fact, this constraint for each of these different elements is actually a linear function. And so this optimization program that I've written down is a linear program over the space of functions, and as a result is an infinite dimensional linear program. Now, the good news is this linear program, any feasible solution to it is going to generate a W whose one super level set is going to correspond to the forward reachable set of the original system. And in fact, it has a really nice property. That is, if I fix a particular parameter k, and I look at any possible x where wx of k is greater than or equal to 1, well, that's going to correspond to the trajectory parameterized forward reachable set of the system. And in fact, this seems really, really nice. It is really, really nice. The problem is that this is a linear program over the space of functions. And the question is, how do you actually implement this in a nice way? The good news is that for polynomial, rational, and trigonometric dynamics, there exists a sequence of semi-definite programs with vanishing conservatism that actually solve this linear program. And the details of this formulation are described in this archive paper that's been in review for a few months that's down here. And in particular, we can show that any solution to any element of the sequence of semi-definite programs is in fact a polynomial function w whose one super level set for each k is an outer approximation to the forward reachable set under k. Okay? So what does that look like in practice? So if this is my original system, I pick a particular trajectory parameter k star over here. In fact, if I look at the one super level set, I'm now going to get a forward reachable set of the system that is going to describe the behavior of that vehicle under that selection of k star. Okay? And so in fact, what I can do is use these different forward reachable sets under the selection of k star to describe the evolution of the whole system, even in the presence of tracking error, and use that online to actually try to control the system. And I'm going to describe that next. Okay? So now, I have this forward reachable set, I have an obstacle, and now what I want to try to identify are these unsafe trajectory parameters over here on the left-hand side that correspond to trajectory parameters that could potentially cause an accident for me. And in fact, there are really nice ways to actually do this type of optimization. This is what it would look like in this particular instance. Notice I've written this down as a strict inequality. In practice, for this optimization program to work, I would write down something like a 1 minus epsilon here to really ensure that I'd actually satisfied this constraint. Nevertheless, I could actually optimize over any arbitrary cost function. And in fact, the cost function could be over the whole dynamics if I wanted. But the obstacles, in fact, I could represent as semi-definite constraints if I'd like. But the challenge is that if I did that, it would actually run fairly slow at runtime. So if I represented obstacles as boxes, for instance, and I use this type of semi-definite program, we can run it on a really fast computer. And in fact, it would take on the order of about 17.5 seconds, which is really, really slow. Okay. Now, you may think to yourself, well, look, boxes are maybe not the ideal way to represent obstacles. Instead, think of them as a series of lines that describe the effect of a box. Now, even that can be too slow. And so, boxes don't work, lines don't work. The obvious next idea is to try points. Now, points have some problems with them. So let's say I take my obstacle now on the right-hand side, and I discretize it as a set of points. Well, the challenge is that I'm generating sort of inner approximations in that instance to the true unsafe trajectory parameters. And that potentially can be problematic for me, right? I would now run into an obstacle now if I chose from the complement of this representation in the trajectory parameter space. So the way that people think about typically solving this problem is by buffering the system, or buffering the obstacles by some amount. And so if I buffer the obstacles by some amount and then I sample from that space, well, what I hope is that I'm actually generating an outer approximation to the unsafe trajectory parameters, right? And if I can figure out how to do this buffering and then discretization of the set, maybe I can develop a representation for the unsafe trajectory parameters that would be amenable to doing real-time optimization. And in fact, my students in this paper down here at the bottom have actually shown how to do this while assuming that the vehicle is convex and that the obstacles can be arbitrary but are buffered by some distance d. And then they've shown how to construct a point spacing that can be computed offline that generates an outer approximation as desired to the set of safe trajectory parameters. And in fact, this theorem and this construction are described in general in this paper down here, but we can show what it looks like in the case of a car here, and I'll show you what it looks like in this example. So let's say my car has a finite width. Suppose I buffer my obstacles by a width between 0 and 1/2 the total width of the car. Well, if I select a point spacing now that satisfies this requirement up here at the top, which is that the point spacing between between points on that buffered obstacle representation are less than or equal to 2b, well then, in fact, we can show for rectangular cars in this instance that we actually are generating an outer approximation to the unsafe trajectory parameters. And in fact, what that means in practice is that if I choose points on this discretized obstacle representation, and for a particular trajectory parameter, it's less than 1, then in fact, the autonomous vehicle actually avoids this obstacle. And in fact, we've provided a constructive procedure, not just for rectangular objects, but objects in general that are convex, okay? So what does this look like online? Well, there's one last piece that we need to think about, and that is that time horizon over which we're actually generating or representing this forward reachable set. And we need to specify that time horizon correctly in order to ensure persistent feasibility, that is, that we can always generate a behavior for the system that is actually safe. So what we're going to assume is that our planning time is fixed and bounded, and we're going to assume that we have a maximum stopping distance. And in fact, I should have mentioned in this portion of the talk, we're really going to focus on obstacles that are static. And I'll talk about how to actually generalize this to moving obstacles in a movement. But in this instance, in order to make guarantees about safety in the static context, we'll make these two assumptions. And in fact, we'll assume that that time of planning basically corresponds to some length of time. And what's going on is that I'm applying, in this instance, the control input that I've generated at some previous instance in time as I'm actually constructing a particular plan during this tau plan that I have. Now, the thing is that may happen is that as I'm doing my planning, what may happen is that I find that I have no feasible solution to my optimization problem at runtime. And so what I'll do then is make sure that I always have the ability to come to a stop in any plan that I generate. And that's actually providing a lower bound on the time horizon over which I actually need to plan. The one last thing that we need to think about when we generate this planning horizon is how large of a sensing horizon do we actually have? And in order for this to actually work out, we need to make sure that our sensing horizon is greater than or equal to 2 times that tau plan plus tau stop. But if we select our planning horizon, capital T, as being greater than or equal to tau plan plus tau stop, well, then we can always ensure that we have a safe trajectory, either the one that we generate from the optimization problem, which always ends in a fail-safe maneuver, which is braking and coming to a stop, or applying the new plan that we've generated from our optimization problem that I described earlier. Okay, so this is a high-level description of how this algorithm works. Obviously, all the details can be found in this archive paper. But what does this look like when we're actually solving this problem at runtime? Well, here's an illustration of what it looks like in a simulation environment. So this is a 5-dimensional unicycle model or Segway model. And in fact, what we're doing is running this optimization at runtime, and it's actually selecting elements from this trajectory parameter space and then illustrating what the forward reachable set looks like in green, that is, again, generating online. And what we've shown here is a buffered obstacle representation. The buffer is actually fairly small in this instance. And all of these different points are actually that point discretization that we've shown how to select in this instance to actually guarantee the safety of the system while it's doing optimization online. And so the thing we wanted to try to do is to understand if this was actually a good idea. And the question that most people have is, well, look, you're bounding, the behavior of the system, that is the difference between the original system and this trajectory planning system. And potentially you're generating a really conservative representation because you're solving a semi-definite program that's generating an outer approximation. Is this truly tight enough for you to actually be able to improve the quality of solutions as opposed to the standard ways that people think about doing planning for these types of systems? And so in order to do that, we wanted to make sure that we did a fair comparison. And so we actually applied sort of two different algorithms here. One was an RRT. It was based on this paper down here, which I think came out of sort of the Grand Challenge folks. And then this other algorithm is a nonlinear model predictive control algorithm. We didn't have, we could build our own implementation, but we wanted to try to use a standard implementation. So we used an implementation based on GPOPs, or that is, we use GPOPs too, which is a commercially available software developed by Patterson and Rao from the University of Florida. It allows you to basically translate your optimization problem using pseudo-spectral optimal control into something that you can solve online, or you can solve using MATLAB. And in fact, the thing we wanted to first figure out is like the right way to represent obstacles. And again, most methods buffer their obstacles in order to make some guarantee about safety. And so what we did was actually look over sort of different obstacle discretizations in order to compare these two different methods and find the best possible representation for each of these methods. And in fact, it's not too surprising. That is, as you increase the size of these buffers, basically you start becoming more and more safe. That is, you have fewer and fewer crashes. But the trade-off you make is because the obstacles now look much bigger than they actually are, you're not actually able to reach the goals that your high-level planner has actually handed you. That sort of intuitively makes sense. And in fact, this has been sort of realized even in the autonomous vehicle sort of deployments that we've seen out in the real world. So many people have commented that these Google cars, for instance, are really, really conservative, that they tend to behave in a way that a human being would not behave. And I'd argue that the reason that this is happening is because they've actually taken their representations of the environment and essentially buffered them, either by using a computer vision algorithm that is maybe a little bit conservative, or actually physically represented them while planning by using a larger representation than is actually required, to truly make sure that they are safe. So what we did was basically run this over 10,000 different scenarios in simulation using a 5-dimensional unicycle model similar to the one that I illustrated earlier. And we basically fixed our tau plan as being a half a second. We fixed a sensing horizon, and we ran our planners all against one another. So RTD, the algorithm that I described here, actually got to the most goals. So 87% of the time it got to a goal. Importantly, it had no crashes. RRT in this instance was able to get to a lot of goals as well, but it had some crashes in this instance. The nonlinear model predictive control algorithm, that is GPOPs2 in this instance, it was really slow. So in fact, with this planning horizon of a half a second, it wasn't actually ever able to generate plans consistently enough to actually get it towards a goal. Now, when we increase the planning horizon by a little bit, in fact, it actually does a little bit better. That is, it can actually get to more goals. This is described in this paper. The trade-off here is as the planning horizon becomes larger, it means that you need to sense over a much larger horizon, and you need to potentially incorporate that into your braking distance, et cetera. And that means that typically speaking, it can be sort of more burdensome on perception algorithms or prediction algorithms. So that's sort of the trade-off here for these nonlinear model predictive control thing. So the final comparison we wanted to do was to try to compare this to FastTrack. And if you recall, FastTrack basically treats its trajectory planner as if it's a disturbance into the system that its trajectory follower then tries to actually track regardless of that disturbance, again, by solving this sort of HJV style equation. And in fact, unsurprisingly, what we show is that both of these methods actually avoid crashes, but our method is actually significantly less conservative because it's actually treating the trajectory planner as being sort of not just some sort of disturbance into the system, but something that is working in concert with the trajectory follower, okay? And in fact, we've shown that this works on a variety of different hardware platforms. So again, I'll mention, you can find the YouTube link to these videos down here. What I wanted to show here, and what my students wanted to show here, is that we could actually do a single cut video where we would actually just keep throwing obstacles that the system did not know about in real time in front of it, or before a priori in front of it, and then the Segway will turn around. It has a finite sensing horizon, and it's actually going to figure out where these obstacles are as it's seeing them and actually move around them in a way that can make guarantees about safety, right? And this video keeps going on and on. In fact, it's really funny. You'll see that basically setting up the environments is running at 16x, but the system is actually, the video is playing at 1x. This video is 5 minutes long, but what you're going to see is that even this, this implementation is actually still able to guarantee the safety of the system without sort of making any a priori assumptions about what the obstacles look like or where they're going to appear in the world. And, you know, this video, if you look down here, will keep increasing the difficulty of these scenarios as we go along. I'll sort of jump to the end here. And you'll see that eventually my students feel so confident that they actually start standing in front of the system, and actually it's able to nicely go around them regardless of this. So in fact, we've actually extended this to a full-on Carson model. So this is a full powertrain model of a Ford Fusion that we actually have access to at the University of Michigan. And in fact, this is an illustration of it in the Carson simulation. This is in M-City, which is a test track that we have access to at the University of Michigan. And in fact, what you're going to see here in simulation is that it can get up to about 35 miles per hour or about 60 kph, and it's able to avoid obstacles and as it's sensing them online. And it behaves sort of like a human being would behave. That is, if it starts seeing an obstacle that is problematic, it starts slowing down if it needs to make a lane change, et cetera. And it's doing that all autonomously. And in fact, the results and the algorithm and the implementation are described in this ACC paper down here on the bottom left. What we've done more recently is actually show that you can extend this to moving obstacles. In this instance, we don't use that function W, but we use that function V that also is generated by that optimization problem, the one that looks like a Lyapunov function. And that V is shown in green down here. And in fact, in these simulation environments, it's able to execute things like left turns, which have turned out to be sort of the most cumbersome problem for these types of autonomous vehicle platforms. And in this instance, we don't make guarantees about safety because, again, we could be parked and someone could run into us. But instead, we developed this novel notion called not at fault. And we actually talk about generating behaviors that are not at fault. And you'll see in these simulation environments, again, we're able to generate not at fault behavior, which means that we come to a stop and we allow everything around us to also come to a stop given a finite reaction time, which we assume exists a priori. Okay. And in fact, we've shown this actually works on a real system. This paper in RSS 2019 describes the implementation. Again, the video of this implementation can be found on this YouTube link on the bottom right. And this is at the University of Sydney. And in fact, they're using this taxi service with our planner currently. Well, they were until they shut down. To actually, shepherd people around their campus. And in fact, this operates about at 5 meters per second, which is about as fast as a human being would feel comfortable driving it in these sort of congested environments. Again, as I mentioned, we've extended this to a variety of different systems. And in fact, we're working with Ford to actually apply this on their Ford Fusion in the idea or in anticipation of them actually trying to deploy it as a feature in their new vehicles as they're coming out in the 2020s. And so the last thing I'll mention is that we've actually extended this, as I showed earlier, to a variety of different systems. I mentioned the quadrotor example, but we've also extended this to the ARM example. And in this instance, the question most people ask is, well, look, you're trying to generate these reachable sets. That tends to be really hard for high-dimensional systems, for nonlinear high-dimensional systems. How are you doing it? And in this instance, we have a really simple idea that leverages that trajectory parameterized representation of a reachable set. And the way that it does it is by generating different forward reachable sets for each of the different joints of the system and essentially stacking them up in a way that allows us to essentially take one reachable set for each joint and then essentially append them to one another, and allows us to generate a full forward reachable set for the system that is, again, trajectory parameterized by the trajectory parameter for each of the different joints. And that essentially allows us to build a reachable set representation that, again, we can use online in a nice way, as I described earlier. We call these two procedures slicing and stacking. And what this allows us to do is essentially generate high-dimensional parameterized reachable sets of an arm by just building parameterized reachable sets for each joint individually. Okay, and in fact, it allows us to build really tight reachable sets. So over here on the right-hand side, in gray, you're actually going to see what the forward reachable set looks like. In blue, you're actually going to see what the actual state of the arm is. In black, you're going to see high-level waypoints that are generated by a high-level planner. And in fact, that high-level planner is going to sometimes generate waypoints that are in collision. Note that for manipulation folks, these types of tight, tight systems, meaning constraints that look really, really small, tend to be the really hard ones for them to make guarantees about safety. In fact, we can still make guarantees about safety for these types of systems. Oh, I guess the video jumped ahead. But if you go take a look at the video down here, you'll see us actually generating safe plans even in the instance where we have really, really small sort of unsafe or really, really small constraint sets that we're trying to avoid. And in fact, let me jump ahead. We can, again, apply this in dynamic environments. So again, you'll see sort of an obstacle appearing here, like a vase. And again, the arm is figuring out at runtime how to actually avoid this obstacle that it's only sensing when the obstacle appears. One last thing I'll mention is that typically people look at this optimization problem and they say, well, look, you're still having to solve a nonlinear program at runtime in order to find that trajectory parameter. What we've been able to do is recently develop algorithms that solve this polynomial optimization problem while making guarantees not only on the time it takes to run the algorithm, but the quality of solution that you're capable of generating. And so here's a really difficult scenario. And what you're going to see, is that solving that trajectory planning problem with the safe sets at runtime using a typical nonlinear programming solver like IPOPT or SNOP, you can still make guarantees about safety, but you're going to find potentially really bad solutions because it's really hard to solve these problems. And this algorithm that we've developed that you can find access to down here, here's the GitHub link, here's the videos. What it allows us to do is essentially solve these same types of optimization problems with guarantees about the quality of solution and the runtime it takes to solve this problem. And Shreyas is obviously really excited. It took a bunch of work to make this work. And it's a really nice implementation that you can find access to down here. So it's a lot of details. I'm now going to move to the second portion of my talk, but I'm realizing that it's already 11:50. So maybe I'll pause here and take some questions. And then if there's some time left, I can move on to the next portion of my talk.
It looks like we have a question from Joe, so I'll unmute him.
Yeah, I was wondering, how do you account for disturbances in this? It seems like you're mainly focused on like the controller, the tracking, and the location of the obstacles. Obviously, you can't do anything if the car gets sideswiped, but there's going to be some other disturbances. Are those included in some bounding parameter or some other way?
Yeah, so that's a really great question. So we've actually thought about it in several different ways. So for instance, if we were driving on ice, as I showed earlier, can we actually incorporate that in a way where we have some uncertainty around what that trajectory or that friction constant actually looks like, and actually incorporate that into some sort of probabilistic reachable set? So we don't have any papers out on that, but one of our students is pretty close to writing a paper on that idea, which is building a similar type of probabilistic representation of this style of problem that we're solving. If you wanted to be extraordinarily conservative, you could obviously just incorporate that into that G function that I described earlier as like an additional disturbance that would increase sort of the size of that bounding function. That may be potentially prohibitive, so that could be problematic. The other option is to potentially incorporate that sort of uncertainty that maybe you're figuring out at runtime as an additional trajectory parameter that is sort of fixed, right? So that is, if I know that I'm about to drive over black ice, I can actually incorporate the friction constant associated with black ice as an additional trajectory parameter that I sort of constrain at runtime to basically build a forward reachable set that is conservative enough to account for the fact that I'm driving over black ice at this instance in time. And in fact, we've done that for the systems that we play around with, which is we are able to estimate certain uncertainties or disturbances that appear on the system at runtime and utilize that in our representation directly.
I have one question about the G function. So, as you know, it seems like a lot of the hardness here is analyzing the full dimensional system, right? Which you're trying to avoid with the reduced order system. Don't you have to solve that hard problem on the full order system to find a G?
So that's a really good question. So in fact, you do if you so like the sums of squares optimization formulations for this problem typically try to solve a version of that, which is, hey, I want to actually somehow find both the tracking controller and find a G function that is a function of my full state of the system. There's some good news on that. So we have gotten better at building those G functions in a way where we can satisfy that assumption directly, and it doesn't necessarily have all of the problems of having to hold on to the full dimensional system directly. I can talk about that sort of maybe offline, but like the idea then is that instead of like solving a forward reachable set description of the full dimensional dynamical system in the sums of squares optimization problem, I instead pre-compute what those trajectories actually look like by somehow building like a control representation for that system, for the high dimensional system a priori. So That's one route. The other route we've done is actually figure out better ways to sample the system so that we can build those bounds without having to solve a sums of squares optimization program. So that DSCC paper that I described, and maybe I'll do the following, which is if you take a look at so this type of quadrotor system. For these types of quadrotor systems, there's really nice ways to describe how these disturbances typically appear, or the difference between a high dimensional model and low dimensional model actually look. And for instance, if we have this rotation matrix that's describing the orientation of the system, there may be really nice ways for me to make an assumption about how fast the rotation dynamics work as opposed to the translation dynamics. And that allows us to more effectively characterize the lower dimensional system and sample over it in order to approximate that G function better. So that allows us to avoid solving that sums of squares program over the high dimensional system directly. The last thing I'll mention is that, in fact, we've gotten better at solving those high dimensional sums of squares programs by leveraging some structure in the system, which is, maybe there's some sort of chain structure inside of the system that we can leverage in order to build this G function more cleverly. So I know that, Jean Lasserre from France has been developing some really nice tools on computing regions of attractions of systems that have sort of chained dynamics. And we've been using those types of systems, or those types of formulations, to also generate these G functions as well.
Thanks. We also have a question from chat here.
Sure.
I don't know if you can see it or I can read it.
Do you want to read it?
Yeah, sure. The question is, can you talk a little bit more about the concept of not at fault? I feel like the animation where your agent comes to a complete stop in the middle of the intersection and assuming the oncoming car will stay on its trajectory perfectly might not really be, quote unquote, not at fault in a common sense sort of way.
Yeah, so that's a really good point. So in that instance, the right way to execute that left turn trajectory is to make sure that any trajectory that you execute actually has to go through the full intersection. And in fact, we've built extensions that actually make sure that you do that. So it won't partially execute a left turn, right? But nevertheless, I think the real sort of meat of that question is, well, look, without having incorporated some description of what the interaction looks like between an individual and the pedestrians, or this autonomous vehicle and the pedestrians that are around it, or the other vehicles that are around it, you're not really going to be able to meaningfully engage on like what it means to be safe in this instance. I think that is a really valid comment. And I really think that gets into sort of the next things that my group is looking at, which is, can we now meaningfully incorporate things like interaction constraints inside of our optimization problem? So right now, the way that we're solving this optimization problem is we actually have predictions of what the person is actually going to do. We don't actually have those predictions as a function of like some sort of interaction or interactive behavior of what our autonomous vehicle does. And so what you can think about doing is, while you generate these sort of reachable sets that are a function of the trajectory parameter, you can also have reachable sets that are a function of what you expect that the other person's response will be to the parameter that you choose. And I think that's a really interesting idea. We have not done that yet, but that is certainly something we're looking at. So I don't know, Michael, how much time do I have left? We're supposed to end at noon, right?
11:58 on my clock here, so maybe a couple of minutes if you want to. Sorry, we stole your number 2 here with a question.
No, that's totally okay. I'll just mention at a high level what we've been able to do, which is a really nice way to basically use Koopman-based modeling, which is another type of lifting, to actually control soft robotic systems. So I'll sort of jump here to sort of the meat of this, which is basically that we can sort of represent dynamical systems using this Koopman operator representation, which can be identified by solving a linear regression problem. And in particular, by forming sort of this lifting operation, which is taking a finite dimensional state-space representation of a system into like an infinite dimensional space of functions, we can actually identify a linear time invariant sort of representation for our system now over sort of lifted functional representations of the states of our system. And in fact, what that allows us to do is to solve linear model predictive control problems at runtime in order to control the system. But it also allows us to identify linear models of a system that we can say are accurate. And so we've actually applied this to a bunch of different systems. but these soft robot systems are particularly attractive because, learning a model for them can be done in a nice way, in a safe way, but we can still allow ourselves to solve control problems in a NPC style way that allows us to do real-time style things. We've actually extended it to incorporate loading that may not be able to be estimated online, and that can be solved by solving sort of a typical type of observer design that you would try to do if you were in a linear systems and finite dimension situation. And in fact, we can do this really nice demo of being able to sort objects that we may not know a priori. And in fact, the really exciting thing is that this is sort of the first example of doing soft robot pick and place that we've seen. And again, the model learning, everything is done online. And then once we have that model representation, we can actually use it in a nice way. Again, you can see the video down here. The details are in this archive paper. And that's sort of it. I should again mention that these are the folks who actually do all the heavy lifting and the real work. These are the sponsors who've been sponsoring a lot of this work. And in fact, you can find access to all of the code that I described in this talk at these links down here. And again, the takeaways here is this RTD style, thinking about collision-free or not at fault behavior, and this lifting style approach, which I didn't get to talk about in too much detail, to develop convex programming amenable representations for real-time control of soft robotic systems. So I'll stop there. Thank you again for letting me do this virtually. And if you have any questions, I'm happy to answer them.
Thank you, Ron. For the virtual class. Do we have any questions on it? I guess I have one. I know you kind of blew through it at the end. Do you find that you need to be especially clever with picking your basis functions for the work with Koopman operators?
Yeah, so that's a really, really great point. And actually, I'm also seeing a question on that Leakin posted. I'll answer that in a second. So in fact, for these examples, not really, which is we have not had to be particularly clever in choosing the basis functions that we use to do lifting. What we've done sort of inside, in tangent to this, is thinking harder about what are the right ways to do this lifting, meaning how do you find those basis functions intelligently? I won't say too much, but I think we've made some progress on that side for general systems. Like how do we look at a particular system and then say something better about the style of lifting that we're doing? I will also mention that the lifting that we're doing here is treating the control input in a linear way. You can show that style of lifting, in fact, for general systems is not going to generate an infinite dimensional representation that may be accurate. In the case of these soft robots, it tends to be, so that's good news. But for general systems, we can show even simple examples where that may not work out. But we've been working in my group on developing better strategies to deal with those types of situations. It hasn't been an issue in the soft robotics scenario, but for general systems, you can imagine that may be an interesting or attractive feature to consider. The question Leakin asked for Koopman operators, comparing models, fidelity, finite elastic deformation models or finite element analysis? It's a really great question. If you take a look at that archive paper that I posted up, in fact, we do a comparison to those styles of models. So in fact, the student who was working on this, Dan Bruder, he's just about to graduate, but when he started his PhD, I wasn't a soft robotics person, but he was, and he was really excited about building, sort of these types of finite element models. The thing that we found is that some of these models are super, super useful, meaning they're really accurate, but the problem is that they're not amenable to performing real-time control. Meaning, for instance, the control input doesn't appear in the model in a way that allows us to do real-time optimization, for instance. And in fact, we've shown that like these finite elastic deformation models in particular are not necessarily as good at being able to do control-oriented tasks. And some of Dan's earlier work that I didn't describe here, was focused on seeing if we could try to employ those types of models. The finite element ones work a lot better, but they're not as attractive in terms of doing anything real-time, at least in our experience.
That answers my questions.
Ooh. All right, unless there's any last questions, just want to thank you, Ram, again for coming out and doing this virtually. Fantastic talk, enjoyed it a lot. I think everyone else did as well. I think we'll let you go there unless you want to, anyone wants to hang around and chat.
For sure, I can hang around for a few minutes if folks have more questions or want to chat. If not, again, feel free to take those links for the talk. I can post them again just to make sure everyone sees them.
They made it into our Slack channel as well, so I think.
Okay. Great.
How are you guys holding up over there through all this?
It's been okay. Ann Arbor, fortunately, has not been particularly badly hit, but Detroit has had a hell of a time with it. And so, they shut down, but it's yeah. I mean, it's bad. 60 miles from here, really bad. 60 miles from here, as I'm sure. Well, the news has been reporting some of it, but yeah, it's been pretty rough out there. But our students are doing fun things to try to make this, to find solutions to some of these problems. So like Dan, that student I mentioned, actually built a ventilator that like for $50 and basically posted like all the information online, and like, people are trying their best in this situation, which is good. And frankly, our medical school has been like, stop helping us because, we are like overwhelmed with the amount of help that we've been getting. And so it's been a funny response to some of these problems, but yeah. You got, how old is your kid now? Must be like 2?
18 months now, yeah.
18 months, okay. Name again?
Serafina.
Great. How's it going?
Oh, it's good. Yeah. I'm sure anyone in the chat who's in my lab or my class has probably seen her plenty of times or heard her yelling in the background. But yeah, that's been a challenge. But,
your wife was working as a nurse, right?
Yeah, she works in mental health. So she's actually moved all of her does outpatient work. So everything is done remotely now.
That's great. That's great.
Okay. The easy transition in that
That's
sense.
helpful. I mean, it's if you can avoid this thing, it's good.
Yeah.
It's funny. I've had a few friends who are ER folks, and they've all sort of weirdly been exposed and whatnot, and like their life at the moment seems crazy to me. So
yeah. So yeah, fortunately for us, I suppose she's not inpatient or not working in.
That's good. How's your Cassie doing?
It's going. I mean, it's sitting in the lab right now. I went down to charge the battery yesterday. That was my I think we have a couple of students now. Looks like neither of them in the chat here anymore, but who are working on Lego locomotion projects. The things we're most active right now is thinking about design of reduced order models, and that's something I think that we've talked about a bit in the past. So Yiming has been working on that, and how do you optimize a low order model to be effective across a space of trajectories or tasks, really. Mm-hmm. And then the other thing that sort of more basic level, we're thinking about uncertainty and impacts for locomotion. And
nice.
The basic question, right, is everyone who's walking uses some sort of hack, right around the footfall timing. Mm-hmm. They like blend the controllers, or they do something, right? And we want to understand why those hacks are useful and appropriate, and then from a what's a simple description of uncertainty there that necessitates these control strategies that matches data, and then can you do something better with that notion of uncertainty?
Sure, that's really interesting. Huh. So have you guys figured out what you're doing with dynamic walking? Speaking of walking.
Yeah, we're going to do it remotely. We haven't figured out the exact format yet. So it's going to be a one-day remote event. Aaron was on the chat. He came to watch, and Joe was one of his students who asked the question.
Okay.
So we haven't settled on the exact format yet, and the technology. That's something we're investigating right now. If you have any thoughts on what is the best tool to make it interactive and engaging?
Yeah, so the funky thing about doing this Zoom things is like you're basically so focused on your slides that like you just are not. It's like there's no video. I almost feel like the thing you should. I mean, and this is cumbersome, but like the thing you should force everyone to do is to actually show themselves in the video.
Yeah.
And like that way, at least it feels a little bit more interactive.
Yeah, and that helps for the talks for sure.
I mean, I think it can make the conversation feel a little bit less less awkward, at least.
Oh yeah, I mean, I'm sure you get this when lecturing too. I don't know if you're teaching a semester, but like
I am. But
lecturing to a group of black boxes is rough.
You know, well, here's a fun idea that one person in my department had, which for better or worse may not be what we want to do with dynamic walking, but actually may be, which is he basically taught his entire undergraduate lecture on Twitch. Okay. And like, he was like, actually, it was way better than Zoom or Blue Jeans or anything. And he was like, it's much easier to interact with people via Twitch. And I was like, that doesn't seem true. But then I was like looking around, I was watching some streams. I'm like, oh, I can see why this works a little bit better.
Thinking about Twitch, why is Twitch better?
Well, I think you're seeing the stuff on the right-hand side as you're giving the talk, I think a little bit more clearly. But I also think there's ways to like more clearly say what you're saying. I don't know. You should fool around with it. It feels a little bit more natural. And it's easier to do larger things on that, I think, than Zoom.
Yeah, we were thinking something like for the talk, something like Zoom, but simul-streamed to either YouTube or Twitch or something like that. So we have, we can get like the quote-unquote attendees in Zoom and they can interact. But if there's a larger global audience that wants to tune in, they can do so without overloading the Zoom. But the other thing, I think that's a harder question is how do you do things like a poster session, things like coffee break, where we were looking at like VR tools like Mozilla Hubs and something like that, which could work, but I don't know. We'll see.
The funny thing is, I imagine if you actually sent an email to the entire group and just asked them, like, how should we do coffee breaks? I'm sure you'd get like a dozen ideas that are just like completely out of the box and interesting. I think the Oculus Rift idea of just like everyone wearing a VR headset, it would be interesting.
Well, yeah. When I say VR, I don't mean like, you could do that, right? If you have one, but just like there's some like virtual environments where you have a little avatar and you walk around and you can actually like see these environments with images of posters and videos and stuff for people. Like if someone is willing to go in and spend 2 hours assembling or 3 hours assembling their little VR world for the poster, it can be kind of neat.
So my wife's parents are also professors, and my wife's dad is just a tech nerd. And so he actually went to Second Life and created, my mother-in-law is she's a Japanese professor. And so like she teaches a bunch of intro Japanese courses and whatnot. And so he basically created an entire Japanese like environment in Second Life that like you can go to learn words and whatnot. And apparently it's been a hit. So like, I think your idea there of like trying to do that in a poster session could be pretty fun. But yeah.
Second Life, that's interesting. Okay. I don't know anything about it, but I've heard.
I don't either. I hear this from him, and he was like, "It's been really great." And I was like, "That's actually kind of an interesting idea." I could imagine that actually working for dynamic walking potentially. If you want, I can connect you with him to like tell you his experience if you would think that would be useful. So.
Oh, let me maybe let me Google it first and see if it's like a first pass.
No pressure. Just let me know if you're interested. Just spinning ideas. There is someone here, Gabriella, by the way, that is from, I guess, UC San Diego, Zichao Lee, who's asking me for a link to the video. You'll be able to send that, right?
I will post it as soon as you give me that release file.
Okay, great. I'll sign that, and then you'll be set, Zichao, if you're still listening.
I think he's still here. And Gabby, I started recording at some point after I know you crashed, so. Maybe, I don't know.
Hopefully it worked out, but I think that'll be helpful if you send me that.
Okay. I recorded to the cloud. I don't know if that means my cloud or your cloud, but
I think it's your cloud. But you can just give me a link, I think, and it should work.
Yeah, we'll do.
All right. There's no other questions. Thanks guys. I really appreciate it. And Michael, if you have any comments or questions or whatnot or suggestions, please send them my way.
Yeah, I'd love to chat at some point. We can maybe find a time just to ask questions or something. But I enjoyed the talk. I think the work on combining the simple model with the complex model looks really fascinating. I want to learn more. Is there one you'd recommend looking at? Is it the DSSC paper or something?
Yes, I mean, that one describes it in the quadrotor context. It's probably a really nice way to like think about how we're building these bounds. Yeah, so yeah, I would take a look there. It's a nice explanation. There's like an extended version where they walk through how to actually do it.
Okay.
And that paper by Murat's group is also a nice one. So if you take a look at that, he has some Sumzo Square stuff that he's been pitching around this. But yeah.
Will do.
Cool.
All right. Good to talk, Ron.
Thank you guys.
Good to see you.
Bye.
Thank you so much. Have a good day. Bye.